Hello everyone, welcome to DrZ Academy. In today's video, we are going to talk about the geometric distribution. Alright, so let's start. Consider the definition, right? So let's see that we have a sequence of independent Bernoulli trials with the same probability of success, P. Right? So let X be the number of trials up to and including the first success. Okay, then X is said to have a geometric distribution with parameter P. Okay, so the probability mass function will be what? P of X equals, probability for X equals X is 1 minus P raised to the power X minus 1 times P. So because they're independent, right? So now probability for X equals X. So basically you need to have failure, 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 and then success, right? So success. And then how many failures are here, right? So in total, we know that's X, but before the success, you need to have X minus 1 failures. So they're all independent. So that's why you have what? The probability of failure 1 minus P raised to the power X minus 1. And then times P, right? So that's the probability for X equals P. All right, so that's the geometric distribution. And for a geometric distribution, we have the following cumulative distribution function, right? So that this one is the probability mass function. Now here is the cumulative distribution function. So it's defined for X less or equal than X equals, here equals this one. So especially when X is integer, positive integer. All right, that is a positive integer, okay? Integer, or it's better to have the if X is a positive integer. Okay, so now if X is not an integer, so f of X is going to be what? Probability X less or equal than X, right? The equals what? The probability for X less or equal than the integer part of X, right? So it's better to write in this way. It's 1 minus P to the integer part of X, right? So that would be better. Okay, so this will be defined for all X in R. Okay, so now how to prove this one? So this is pretty easy, right? So 1 times 1 minus P times this one, so you can do a geometric sequence, and you can find that it equals this one. All right, so that's the cumulative distribution function, right, which is given here, right? So not this one. Now the survival function is the probability for X greater than X, which is 1 minus f of X. Right, so which equals what? 1 minus P right, so equals what? 1 minus P X, right? So that's going to be the survival function. Okay, so here again, this is for X being a positive integer, right? So positive integer. Now here, this is going to be for all X in R, right? So this is better, okay? So this is the cumulative distribution function and the survival function for geometric distribution. Now the moment generating function is going to be what? As you can see, right? So expectation of e to the power t, okay, e to the power tx, so equal to the summation of this one. All right, so now you can just take this summation, all right, x equals 1 to infinity, but e to the power t times e to the power tx minus 1, right? So, and then 1 minus P X minus 1 times P, right? So, which is the same as summation X equal to 1 to infinity, all right? So, e to the power t, okay, going to be what? 1 minus p parenthesis in bracket e to the power t x minus 1 and times p, right? So actually p and this one are constants, so you can take it to the front, right? E to the power t summation x, well, now you can do this equal to 1 to infinity 1 minus p, all right? So e to the power t x minus 1 times p, so which is exactly this one, right? So you got that. And then using geometric series, you can find that it equals this guy, and it equals this. Now this is holds if what? For t less than ln 1 minus p, which is good for in the neighborhood of 0. Yes, in the neighborhood of 0, because this is going to be greater than 0. So therefore, the moment generating function exists for this geometric distribution. All right. So now for the moment generating from this moment generating function, we can find expectation is 1 over p, and variance is 1 minus p over p squared. So basically, you can find the okay. So I'm not going to do that here, all right, but you can find npt first derivative, right? So and then find mx second derivative. All right. So you will be able to find this one equals. All right. So m prime of 0 and expect variance. All right, so you can variance of x equals expectation of x squared second moment minus the this one square. All right, so it's going to be 1 minus p over p squared. Now I'm not going to do that here. All right, so but you can find this one. All right, so but this is going to be the expectation and the variance for geometric distribution. Okay, so 1 over p is the expectation, variance is 1 minus p over p squared. Okay, so now let's there is an alternative definition. All right, so in some textbooks they use this definition. Right, an alternative definition of geometric distribution is the random variable y, which is the number of Bernoulli trials before. Okay, so before the first success. Okay, so the support of y now become what? 0, 1, 2, 3, to infinity. Y is related to x, right? So because x is up to and including, right? So but y is before, right? So x is going to be what? Y plus 1. And the probability mass function of y is going to be, all right, so p of y is y equal to y, so x is going to be y plus 1, so you can just plug in, you can find this one, right? Expectation is going to be x minus 1, 1 minus p minus 1, so it's this one, and the variance is going to be the same, right? Variance is going to be the same. Now, similarly, the moment generating function is going to be, so you can rearrange it, well, there is no e to the power t, right? So, because what? Y equals x minus 1, right? So e to the power negative t times mx of t, right? So, and you will see that it's cancelled out. There is a e to the power t, and it's just cancelled out, right? So, which left to this one. All right, so this is going to be the alternative definition of a geometric distribution. Okay, so very good. Now, when right, so you got to be careful when a geometric distribution appears in the exam P. All right, you got to be careful. It is important to identify the version of it. Is it x? Is the number of trials up to and including the first success, right? Is that x, or is that y? Is the number of trials before, right, the first success. You got to be careful. Now you can do that by checking what the support. If the support is Sx or support is Sy, is 0 possible. Yes, in other words. Now let's consider the following example. In tossing two four-sided dice repeatedly and independently on successive tosses, right? We want to find the probability of getting a match on the teeth toss. All right, so find the expected number of tosses until the first match is tossed. Okay, so now here let solution, right? Let x be the number of tosses up to until, right? And including the first match. Right, so then x, all right, has a geometric distribution with, all right, p equals what? What's the probability of getting a match in doing so? So the sample space, there are I and j, right? So j is 1, 2, 3, and 4, right? So there are 16. The matches will be 1, 1, 2, 2, 3, 3, 4, 4. So 4 out of 16 is 1 over 4, right? So p is 1 over 4. Okay, so now we want to find the probability of getting a match on the teeth toss, right? So that's going to be what? Probability for x equals t, right? Okay, so this is actually the first match, getting the first match. All right, let's consider this one. Getting the first match on the teeth toss. All right, so therefore x equal to t is going to be what? 1 minus p raised to the power t minus 1 times p, right? So equals 1 minus 1/4 t minus 1 times 1 over 4, right? So which equals, so 3 over 4, 3 to the power t minus 1 over 4 t minus 1 times 1 over 4. So which is 3 to the power t minus 1 over 4 to the power t. Yes, that's the probability for x equal to t, right? The expected number of tosses until the first match is tossed is going to be expectation of x is what? 1 over p, and we see that the p is 1 over 4, so this is a 4. Okay, very good. All right, so that's the first example. Now let's consider this example. The moment generating function of a discrete random variable is given here. Now we want to find these ones. Now, one thing about moment generating function, right? So is the moment generating function determines the distribution. All right, so now it's especially for discrete random variables, if you have a moment generating function, then it determines the distribution. All right, so because at least for the distribution, all right, so it's a unique solution. All right, so now we want to see this one. So x of t, of t equals e to the power t 3 minus 2 e to the power t, right? So if you divide by 3 on top and bottom, so it's going to be 1/3 e to the power t divided by 3. 3 over 3 is 1 minus 2 over 3 e to the power t. So which equals what? 1/3 e to the power t 1 minus 1/3 times e to the power t. Now, if you compare this moment generating function to the moment generating we have here, so PET, 1 minus PE to the power t. So this is the geometric distribution with p equal with the parameter p, right? So now you can see here is exactly the same form, right? With p is 1/3. Hence, all right, so x has a moment has a geometric distribution, right, with p equals 1/3, right? P equals 1/3. Now, therefore, we can find that the probability for x less than 4. Now, less than 4 is the same as what? Less or equal than 3, right? So, which equals f of 3, which is 1 minus p, which is 1/3 to the power what? 3. Okay, so which equals, all right, so you can just find this one. 1 minus 2 over 3 in the parentheses, 2 over 3, close parentheses, up to 3. So it's 0.7037. Okay, so that's the probability for x less than 4. Now then the expectation is easy, right? Expectation is 1 over p over 3. That's going to be 3. Variance of x, all right, so it's 1 minus p over p squared, right? So just plug in 1 minus 1/3 over 1 over 9, right? So that's the square of p. So that's going to be what? Times 9 on top of 9 minus 3, that's 6, right? So we have this. This is expectation, and this is the probability. Okay, so very good. Now let's consider another example, right? It's a probability that a machine produces a defective item is 0.1. Each item is checked as it is produced. Assume these are independent trials. Find the probability of at least 10 items must be checked to find one that is defective. Okay, so now you got to understand this one. At least 10 must be checked, right? So solution, right? Solution. So let x be the number of products checked up to and including the first, right, defective one. All right, so now the probability of at least 10 items must be checked. All right, so the probability at least 10 must be checked, right? Must be checked. It's going to be what? It's the same as the probability for x, what? Is greater or equal than 10. All right, greater or equal than 10. Is that right? So at least 10 must be checked to find one that is defective, right? So at least 10. So x must be greater or equal than 10, right? So that's to find one that is defective. All right, so now how to find this one? So this is actually equals what? The probability for x greater than 9, right? Greater than 9. So, which is the survival function actually, s of 9, right? So, which equals what? Which equals, as we know, 1 minus p raised to power x, which is power 9. So P is what? 0.1, right? So, okay. Here, it's better to say X, it's better to claim here, right? So before we do that, X has a geometric distribution with P is 0.1. Okay, so now this one is going to be 1 minus 0.1 raised to power 9. Okay, so that's from this one, 0.9. Okay, sorry, 0.9 raised to power 9. Okay, so 0.3874. Okay, so that's the probability of this one, right? So very good. All right. Okay, that's about this section about geometric distribution. Now, geometric distribution is also a common discrete distribution that appears in the exam P, SOA exam. All right. So you better to understand the distribution, the moment generating function, the cumulative distribution function, the survival function, expectation, variances, and so on, right? So about the geometric distribution. All right, so that's all about this distribution, and thank you very much. And if you like this video, please click the like button. And if you think this video will benefit some of your friends, please feel free to share it with your friends. Thank you very much again, and I will see you in the next one. Bye-bye.